So surface modifications, they are the manipulation of surface properties to really control cell material interfaces without altering the bulk properties of the materials. The modification also depends on the material used. So typically we would have a surface and we want to introduce a functional layer on the surface or functional groups. And how do we do it now? We have two different pathways. We can either use chemical modifications or we can use physical modifications. When it comes to chemical modifications, we are mainly looking into covalent attachment of biomolecules, for example, also into functional group generations, because we need certain functional groups on the surface to attach other molecules. In terms of physical modifications, we're rather looking into absorption processes. Let's have a look at a few detailed chemical modifications. If we are lucky and our surface has already some functionalities, for example, carboxylic acids, then we can just use activation processes such as NHS, EDC coupling to introduce different molecules with amine groups. If we don't have these functionalities yet, then we have to do something to our surfaces. Typically what we have to do, we have to activate the surfaces. Through plasma treatment or hydrolysis, we introduce functional groups such as carboxylic acids and amine groups. And then we have two different modification approaches here to introduce polymeric materials. Question first probably is, why would we want to introduce polymers? This is simply because we can easily tune the properties of the surfaces by, for example, introducing hydrophilic polymers or functional polymers, which allow us to introduce an even higher amount of biomolecules or even entrap molecules into this polymer layer, which can be later on released. The two methods we're looking at, it's the grafting on and the grafting from approach. For the grafting to, we use predefined, pre-synthesized polymers, and similar to their EDC NHS coupling strategies, we attach these polymers to the surface to generate a functional layer. When we talk about grafting from, it rather means that we have to introduce initiating groups on our surface, and using these initiating groups, we can now polymerize different monomers and also create this functional layer in a similar way. By having functional polymers, as I said before, we can also introduce other functionalities on top of these polymers. So we cannot only tune, for example, the hydrophilicity of the systems. No, we can also introduce groups which allow us later on to attach certain cell attachment moieties, like RGDs, for example. The second approach is physical modifications. And here it can be as simply as just making use of electrostatic interactions to absorb, for example, growth factors or antibodies. Or we can also absorb different nanoparticles, such as gold nanoparticles, which would help us to improve wettability and also the mechanical and optoelectronical properties. One particular important technique is the layer-by-layer assembly. Similarly, I would like to give you a few more points about this important approach. So the layer-by-layer assembly allows you to pretty much generate multi-layered films, as the name already says, on all kinds of substrates. It can be on planar surfaces, can be on particles, can be on fibers. The materials we typically use for this are also polymers, but also nanoparticles. And the way we generate these films is by depositing our surface into a solution of one of these layers, for example, a positively charged compound. We put this layer on top of a film or the surface, and then we immerse it into a oppositely charged system, negatively charged polymers, for example, and then we repeat this process until we have the desired number of layers. And this layer number also determines the surface properties quite a bit, because we can adjust the thickness, but also the porosity and all these kind of things. As I said before, we can use electrostatic interactions, but also hydrogen bonding, for example, or other host-guest kind of interactions. So now we know how we can make these surfaces. But the question is still, why would we want to do this? I mean, we saw it in the first few slides. There's two different reasons for this. We want surfaces which repel compounds and biomolecules, and we want to make surfaces which actually attract and attach biomolecules such as cells for this. We want surfaces which repel compounds and biomolecules, and we want to make surfaces which actually attract and attach biomolecules such as cells as well. And so we are really trying to modify, to tune the cellular behavior on the surfaces. And one simple way of doing this is by introducing surface charges on the surface. For example, it has been shown that positively charged surfaces can easily interact with cells. This can be done on planar surfaces, where we can see a good cell attachment, but also it can be seen by internalization of nanoparticles of positively charged surfaces. If we have rather neutral surfaces or negatively charged surfaces, this is not the case. The interaction with the cells won't be as high. Of course, what we can also do is we can introduce biomolecules. As I said before, we can use some of these techniques which we discussed before, EDC, NHS coupling, for example. We can put polymers with other functionalities on top, and then introduce functionalities which allow us to really mediate the cell attachment. One standard example, or one very common example, is an RGD. So RGD is an amino acid sequence of arginine, glycine, and aspartate, which allow us to really mimic the extracellular matrix and then trigger the cell attachment. One very important part is also surface topography. Surface topography is a bit different to what we discussed so far. Surface topography looks into not only the surface chemistry, but also especially into surface roughness, surface patterning. And this has been shown to really also induce different kinds of cell responses. The way we typically do this is by using different techniques, such as plasma treatment, chemical, mechanical etching, 3D printing, and different lithography methods. So I hope you learned something about surface modifications today. Surface modifications are really important to control cell material interfaces. The surface modifications, however, also depend on the application and the type of material we want to have the surface modifications on. As we saw, there's a large range of chemical and physical methods available, and also there's different ways of really looking into this cell repellent, but cell attachment properties as well. So far, especially in the context of tissue engineering, what has been done is based on cell adhesion. However, there's also more work needed in cell alignment, migration, and differentiation. And more advanced 3D structures are needed to really better mimic the extracellular matrix. Okay, that's it from me today. Thanks for your attention.
What basic conditions are required to grow human or mammalian cells in vitro? Please fill in the blanks to complete the following statements. If you cannot remember, go back and listen to what Paul has to say about culturing cells in vitro.
So going back to our 2D versus 3D discussion, we know that tissues are more than just flat surfaces. So changing topography would almost be something in between 2D and 3D. I wonder if it's possible to culture cells in 3D. Maybe I should look that up.
I mean, we could also ask Professor Scheiber, maybe?
I think I already found something. Yeah, let's watch this video.
Okay.
Come on, man.
Hi, let me tell you about tissue engineering. I'm Veronica Gladtow from CSIRO. Australia. My research interests are in the extracellular matrix, in particular collagen-based biomaterials and tissue engineering applications. I'm also interested in cell material interactions. At CSIRO, we have tissue engineering activities, in particular in vitro models, such as organoid cultures for nerve and brain conduits, as well as tissue engineering applications in cartilage, neural repair, and wound dressings. For example, a wound repair. So let's move on. What is tissue engineering? So a major healthcare need is the repair and replacement of tissue organs. Currently, we can do that through the replacement of tissues through transplantation of donor tissue and organs, use external devices, for example, such as kidney dialysis machines, or actually implantable materials such as pacemakers. We can also currently move from implantation of a biomaterial device, but moving more towards the future in the area of regenerative medicine and regeneration of tissues. And these can be done through engineered tissues that we have designed in vitro and then implanted, and also bringing together regenerative bioactive tissues. So what is tissue engineering or regenerative medicine? Unlike a biomaterial, tissue engineering is the persuasion of the body to heal itself through the delivery to the appropriate sites of molecular signals, cells, and supporting structures. And in particular, to heal itself with normal functional tissue. So what's the overall concept of engineering? Tissue engineering is really bringing together complementary components, such as cells, which may be stem cells or adult cells, and supporting structures, such as scaffolds. Now, these may be biologically derived, synthetic, or composite materials. With that, it's really important to also introduce chemical and physical signals that render the material functional. This concept is also engineering processing technologies and giving rise to products. And for example, in tissue engineering of a cartilage construct, you would bring appropriate cell types such as chondrocytes with a scaffold such as collagen and introduce growth factors in there to give rise to an engineered cartilage-like material. With all these applications, it is imperative to understand the natural tissue and requirements giving rise to relevant tissue engineered systems. And there's two major areas of tissue engineering. One is in the regeneration of damaged tissues, and there's lots of different opportunities in cardiac, nerve, skin, muscle and bone. With that, also, tissue engineering plays a huge role in modelling of human and animal physiology and the introduction of tissue models to screen for diseases and then also to screen for therapeutic and medicinal screening. And there's a lot of worldwide activity in vitro models for brain, kidney, gastric, and eye, for example, retinal tissue. Now, the path to translation is a challenging one with different aspects to take into account. We need to scale the technology and validate it. Is it like the natural tissue counterpart? With that also comes quality control. Are we able to make the same material over and over again with similar properties? With that also, regulatory aspects come into play. How does a natural tissue composed of different tissues and devices are regulated in different areas? So that is definitely a concern and assurance that you have regulatory aspects associated and taken into account. Again, tissue engineering is an area that can be quite costly. So again, this is something to consider. So in summary, tissue engineering is a continuum approach with technologies driving from the biomaterial through to regenerative medicine and with the end goal of tissue engineering. And with that, I thank you, and hopefully I've given you an insight.
Come on, please. I've turned off the live streaming function, but why does
Into the world of tissue engineering. Thank you.
come on?
Select all terms that apply to tissue engineering. If you're not sure, re-watch this section of the chapter as well as Veronica Glattauer's video.
Okay, that video by Veronica Glattauer makes sense, but how do you make these scaffolds she was talking about?
Well, do you remember what we talked about last time? Preparing different morphologies from polymers?
Yeah.
I bet that they use a similar approach to prepare scaffolds in tissue engineering.
Why?
Let me have a look. Okay, so here it says that the most common types of scaffolds are electrospun mats, foams, films, and hydrogels.
And what do they make all those kind of scaffolds out of?
So electrospinning is charging a liquid drop causing it to form an unstable jet, which further causes it to form nanoscale fibers. Weren't you all about books just a moment ago?
I will never keep up with you using a book. I will be sure to only use peer-reviewed sources.
Good for you.
So, foams are made by casting the biopolymer in solvent into a mold and saturating the solution with salt. Pores form around the salt crystals, creating a porous 3D structure.
So inside the foam, it's almost like they're on curved surfaces. It seems like only hydrogels provide a true 3D environment for the cells.
We keep coming back to hydrogels, and that is no coincidence. They are one of the most important scaffold morphologies for tissue engineering, especially soft tissue and 3D tissue engineering. A unique way to prepare hydrogels is by cryogelining. Check out this video by Professor O'Connor, a leading expert, to learn more.
Hello, my name's Andrea O'Connor. I'm a Professor of Biomedical Engineering and the Head of the Department of Biomedical Engineering at the University of Melbourne in Australia. Thanks for clicking on this video. It's great to have the opportunity to tell you a little bit about our work in cryogels for soft tissue engineering. So in my research laboratory, we work on a lot of different biomaterials and we work closely
Come on!
with medical practitioners and clinicians to develop tissue engineering strategies using biomaterials. So students sometimes ask me how I got into this field. I started with a chemical engineering degree. I have a PhD in chemical engineering, and I've been interested for a long time in how we design materials that will interact with biological molecules, cells and tissues in the ways that we want. And that has led us on to working in tissue engineering, and we're particularly interested in designing materials that allow us to control how cells can be cultured using biomaterials, how we might grow tissues outside the body for things like high throughput drug screening, and then how we can use biomaterials for therapeutic tissue engineering to replace and repair missing tissues in the body. So soft tissue engineering scaffolds have a whole range of different criteria we'd like to meet, and the biomaterials we use should support three-dimensional tissue growth. We're interested in soft vascular tissues generally. We want to encourage the cell and tissue responses that we need for those tissues, and so we need tunable properties, chemical, mechanical and architectural properties that will suit the tissue that we're trying to grow. And these materials should be reproducibly manufacturable and made in scalable ways so they can be practically translated into applications. So one way we can do that is using thermal processing or cryogelation. So it's called cryogelation because we're using a cryogenic freezing process and we're working with hydrogel materials, water swollen polymer networks. So our process, as shown on this slide here, is to take a polymer solution which contains a small amount of a crosslinker, and we use that then in the process. We centrifuge that, add that crosslinker and freeze this system. And when we freeze it, we get separation between the solvent, typically water for a hydrogel system, and the polymer. And this phase separation, as the solvent starts to freeze out, creates a network of ice crystals that will ultimately become the templates for the pores in our scaffold. So this is the thermally induced phase separation part of the freezing process. And then we go through some washing and capping stages to make sure that the surface will be compatible with cells and we don't have residues remaining. And what we end up with is a macroporous hydrogel, where we have a continuous network of polymer and pores that are interconnected that template the ice crystals that formed. We can do this in different geometries like cylinders and rectangles very easily. It's a very scalable process, which is very nice for the kinds of applications we're interested in. And what does it look like inside? Well, what we've been able to show is that you can control the pore size inside these structures very readily. So by changing parameters like the freezing temperature, we can change the porous structure inside. So these red images are confocal microscopy images showing the internal porous structure. The red is the walls of the cryogel. Here we're using hyaluronic acid as an example of a hydrogel system. And you can see that the pore size depends on the freezing temperature. If we go from -16 as the freezing temperature to -12, the pores get larger because it freezes more slowly. If we freeze more quickly at -18, the pores get smaller. Similarly, if we increase the polymer concentration, the pores get smaller again. And in this image on the lower left, you can see this is an environmental scanning electron microscopy image. This gives us some insight that the pores are indeed interconnected. The challenge with electron microscopy is that the sample has to be dried. So the pore size we get is not exactly the same as what we see in the fully hydrated sample under confocal microscopy, but this shows us the interconnections, which is very nice. We can then control the pore morphology, so we can regulate the way that freezing process occurs, and that gives us a lot of control about the structure of the pores inside these gels. And we can do things like add additional pore forming agents to make larger pores. And in this case, we're using foaming, so we're adding air by creating a foam. We're using a surface active polymer. In this case, we're using and we can go through the same, showing really large pores templated from those air bubbles. We can then use these kind of processing parameters to control things like the extent of swelling of the cryogels, their porosity, and importantly, their mechanics. So we can make softer or stiffer cryogels by regulating things like the concentration of the polymer. We've taken this technology then to make cryogels tailored for particular applications. Here I'm showing you an example of a certain part of your eyelid called the tarsus. So we've measured the mechanical properties of this tissue. They weren't known previously. And then we've taken that information and tailored cryogels to match those mechanical properties. And what you can see here is the initial or low strain modulus of the tarsus tissue matches well with some of our cryogel scaffold properties. The final modulus is at a higher strain, didn't match exactly so well, but this low strain value is the one we're really interested in. And we can use these scaffolds, of course, to grow cells, and we've shown that they're compatible with the kinds of cells that we would need for that eyelid reconstruction, as an example. So in conclusion, I hope that you can see this cryogelation platform enables us to tune the properties of scaffolds. We can regulate important things like their pore size, their mechanics, and we can make them very easily. So it's a really scalable manufacturing technique. And we're going on to look at things like how we're going to tailor binding ligand presentation and tune these for different applications. So thanks for your attention, and I hope you enjoy your studies.
But how do you put the cells into the hydrogel?
Okay, so you suspend them in their cell culture media and cast them on top of electrospun scaffolds and foams. And for the hydrogels, you suspend them with the hydrogel and then physically or chemically cross-link it.
I wonder what they make the scaffolds out of. Okay, so in the body, cells are surrounded by something called extracellular matrix. So a common choice for the material is biopolymers that are naturally occurring in the human body. Just from different sources, like you can extract collagen from cow tissue. So to sum it up, you just put the cells on the 3D scaffold and wait until they form tissue.
Well, I don't think that's entirely true, but here it says that it is difficult to seed cells
Come on.
exactly where you want. And as soon as the cells grow or proliferate, the exchange of nutrients and waste becomes increasingly difficult.
Here it says in the human body, the diffusion distance of oxygen is 0.1 to 0.2 millimeters. That is why our capillary networks are so important.
So then, how would they have something like a capillary system in vitro?
Well, further down in this article, they wrote that the pore size
Come on. Oi.
and interconnectivity can be optimized to ensure that fresh media reaches the center of the scaffold. However, it also says that the pore size cannot be too large or the cells just won't grow well.
Well, even so, what if the cells become so dense that they fill the pores? And what about hydrogels that tend to have dense polymer networks?
Why are porous networks so important to 3D tissue culture? Do you remember what Paul said about oxygen diffusion?
Okay. To create more complex culturing environments, such as mechanical stimulation, fluid flow, or electrical stimulation, distinct types of bioreactors are used.
Bioreactors?
Yeah, so they are like super fancy incubators. The most common to use are perfusion bioreactors. Essentially, using a pump, it provides a constant supply of fresh media and gentle fluid flow.
Okay, but would that improve the diffusion into the scaffold enough? I mean, capillaries are like little channels, so the blood would have much less resistance going through the capillaries than through a dense scaffold.
Yeah, I mean, that's a good point. But how would they create little channels inside of the scaffold?
I mean, you can cast hydrogels and sponges into molds, right?
Mm-hmm.
So if that mold had thin little rods, you could just make little channels in it.
That does make sense, but what if the cells grow into the channels or the channels collapse over time?
I don't know. Yeah, no.
Wow, Paul has nothing to say. That's a day I will always remember.
How about I answer that question with another question? What if we put cells that make blood vessels into the channels so then they don't ever collapse?
That's an interesting idea. I mean, the body regrows blood vessels when we cut ourselves, right? Mm. So what if we just implanted one of these in vitro tissues into the body? Would it grow new vessels?
That's a really good point, actually. Maybe we could fix all of your tennis injuries that way. Okay, let's see. We need to regrow cells for your leg, your elbow, your shoulder.
You know, I think I have to go. My class starts in 10 minutes.
Come on, don't be like that. I was just teasing.
No, seriously, I have to go.
All right, I believe you. So see you next time. But bring a book.
Yeah, sure. Bye, Paul.
Bye.
Before trying the question, Christian Bay and Dr. Saleh have prepared an excellent introduction into bioreactors and how the field of additive manufacturing can be used to assist in bioreactor design.
Hi everybody, and very welcome to our new video of additive manufacturing in bioreactors. You know us both. My name is Christian Bay.
And I'm Sahar Salehi.
And we want to give you a short introduction of using additive manufacturing in the discipline of biofabrication and bioreactors.
Yeah, bioreactors are the vessels which can mimic the body condition. They can provide the cells a sterilized condition. They can also provide them defined temperature, pH, and oxygen. We can grow engineered tissue within the bioreactors because they require complex condition. And we can also grow animal cells as well as plant cells. In the bioreactors, as you can see also in these slides, there are various components. We require a pump, we require a bioreactor, and we require a medium reservoir. So how do you fabricate them?
Nice question. If you can see on this slide, here are the components of the bioreactor, and you can see there are various components. We use additive manufacturing because additive manufacturing has tremendous potentials. I've already mentioned in the previous video. In that discipline, using additive manufacturing for bioreactors, we can integrate new functionalities into the bioreactor. For example, integration of some sensors and actuators. On the second side, you can custom-made and tissue-made the bioreactor, not a standard, but only an individualized one. And on the third side, we can design the surface. We can locally design if the bioreactor has to have a smooth surface or a rough surface. What do you think, Sarah? What are these capillary tubes on the left and on the right side of the bioreactor?
That's a great question. Yeah, these are the cannulas which are letting the fluid to flow inside the bioreactors, because we mentioned that the bioreactors are a dynamic culture and they are opposite of the static culture. The advantage of the dynamic culture is that we have a fluid flow inside which is bringing all the time fresh medium with nutrition and oxygens, and it's taking away the byproducts from the cells. So when we have the construct like this picture inside the bioreactor, medium is flowing inside and refreshing all the time the content. One question, how can we actually make sure that everything is going fine inside the reactor?
As you said, the bioreactors are dynamic. So it is very important that we know what are the conditions inside the bioreactor. It's very important to know something about the O2, of the pH, of the lactose, of the glucose, but also the flow of the mass, the flow of the medium, which are pumped into and out of the bioreactor. And these are some potentials about integration of sensors, not only attaching the sensors, but integration of the sensors into the three-dimensional structure of the bioreactor. We can also integrate some actuators into the bioreactors. Can you give us an example?
Yeah, exactly. That's so depending to the type of tissue we are growing inside the bioreactors. So we can also apply a similar loading that they experience in the body. For example, if we have cells from bone tissue, we can also apply compression tests, or we can also let them stretch inside the bioreactor like a skin tissue, or like a neuron and the muscle cells. We can also apply electrical pulses, and like this picture here, we can see the beating of the muscle cells inside the bioreactor. If you remember my last video from the stem cells, that's also one way we can also differentiate the stem cells toward a specific type of the cells or the tissue.
And I think these issues we've mentioned, they're not laying on the street. They are associated with some challenges. For example, we have some challenges facing the material, biological, the sterilization and biocompatibility, but also the automation of the process, the automation of the bioreactors and the laboratory. And these challenges we are facing in an interdisciplinary research project with engineers, with biologists, with chemists, and hoping that we have great solutions for integration additive manufacturing into the bioreactors. We hope that this was an interesting insight about additive manufacturing and bioreactor. Thank you for your attention. See you next time.
Thank you.
Which of the following design considerations are general to all tissues, and which are tissue-specific? drag and drop the tiles into the correct category. Consider what general requirements we learned about for a cell culture and compare them to what properties define the functionality of a tissue. If you can't, watch our expert video on bioreactors.
Emma, you have time for a break?
Just let me finish the sentence, okay? Okay, what's up?
I don't know, I just need to think about something else for a bit. I think I might even be overstudying for this test. Is it possible to overstudy for a test?
Well, I mean, knowing you, I'm sure it is. You tend to drift off into related topics instead of focusing on the one at hand.
Speaking of which, we never finished our research into using those tissue models to repair a wound.
Oh, is this one of your magical books you were talking about? Well, I give you credit for being a self-motivated learner.
Do you remember what we learned about last time in that video by Veronica Glattauer?
Oh, I think it was about tissue engineering. It was something like the combination of cells, scaffolds, and other biological factors to create artificial tissue.
See, you have a good memory too. Anyway, if I understood this book correctly, here, tissue modeling is essentially a specific field within tissue engineering. The classic aim of tissue engineering is to replace or augment damaged tissue. So I guess that tissue models can be implanted.
Okay, but I guess they must design tissue models differently than they design...
Or augment damaged tissue. So I guess that tissue models can be implanted.
Okay, but I guess they must design tissue models differently than they design tissue for implantation, right? Because, for example, the muscle that I tore, it took a few months to heal on its own. Whereas if I would, I don't know, cut myself accidentally, it would heal within weeks. So different tissues heal differently. Wait. Okay, so one of the most important factors in determining regenerative capacity is the presence of stem cells.
Before trying the question, would you like to gain more in-depth knowledge about stem cells with Dr. Salehi?
Hi, thanks for watching this video on stem cell biology. My name is Sahar Salehi from the Department of Biomaterials, University of Bayreuth at Germany. I'm a group leader and my research is on developing biomaterials for tissue engineering and regenerative medicine application and focusing on musculoskeletal tissues. Stem cells are the unspecialized cells which are able to divide many times and they have a possibility of the self-renewal. So that's what makes them different to the adult cells. And as well, they are pluripotent. It means that they can differentiate and become specialized for a specific type of tissue and organs. And they are also able to repair and bring the function back to the tissue which has a defect. The story of the stem cells comes back to 40 years ago when in first time in 1998, the isolation of the cells for the first time was reported. We can find the stem cells pretty much everywhere in the brain, skin, intestine, testicles, and bone marrow and muscles. And that's why we need them everywhere in the body. As soon as a defect is happening or injury, these cells can become again specialized and regenerate part of the tissue. We can also direct the differentiation of the cells. How to direct the differentiation? We can use different kind of factors or a stimulator. For example, from the video of Bioreactor, you remember that we were able to apply external stimulator like electrical and mechanical stimulator. We can also use soluble factors like growth factor as well as insoluble factor like extracellular matrix component. And in this way, we can direct the differentiation and make them specialized for soft tissue like neurons or the hard tissue like bones. There are still challenges and issues about application of the stem cells. For example, where do we get them from? Which sources we are using, or even how many of them we can isolate from tissues. Usually the low number of the cells are gained after the isolation. Therefore, alternative is application of the induced pluripotent stem cells or the iPS cells, which are actually kind of modified adult cells. We can reprogram them by adding factors or genetical modification and make them pluripotent, means that they can again divide in many stages, and they can be also specialized for a specific type of the tissue after injury. There is also a broad application for the stem cells. For example, we can use them for the treatment of diabetes, Alzheimer, Parkinson, or the muscular dystrophy. So in the field of tissue engineering and biofabrication, you can combine the stem cells with materials and also guide them to become a specific type of the tissue and then use them for transplantation in patient. Thanks for watching this video. I hope it's useful for you. And if you're interested in what I do, you can check the homepage of Department of Biomaterials.
Stem cells?
Well, I was getting to that. So most of the cells in our body are adult cells or mature cells. These cells are highly differentiated and stable so that they can reliably perform a function. Stem cells are undifferentiated and do not perform many functions, but they can proliferate well and have the potential to be differentiated into mature cells.
Okay, but how do those cells come and help heal the tissue?
Most tissues have some source of stem cells. The adult cells at the injury site recruit them using cytokines. However, most tissues do not have enough of stem cells to repair large wounds.
Cytokines? I think I remember those from biology class. Aren't cytokines secreted by the damaged blood vessels? But doesn't that mean we're skipping what happens right after the injury, like blood clotting? Then again, it's probably different from tissue to tissue.
Well, I understand your point, but not all injuries involve bleeding. I mean, for example, in overuse injuries like my tennis elbow, there's no concrete injury. So even though I'm sure that the type of injury has an effect on how well it heals, I think we should concentrate more on the inherent healing ability.
So I guess that means we have two types of injuries, with and without bleeding. And several organs and tissues.
More on the inherent healing ability.
So I guess that means we have two types of injuries, with and without bleeding. And several organs and tissues which all heal differently. And what you're suggesting is that the common underlying factor is stem cells and how many the tissue does or doesn't have?
Well, that was the first thing that I found that seems to be general to all types of healing processes. But I'm sure there's more to it than that.
Another major factor is how quickly cells migrate or regenerate. If migration or wound closure is too slow, the cells will essentially give up on healing and scar tissue will fill the remaining wound area.
Okay, and when do the cells give up?
Most of the initial growth occurs within weeks, and the remodeling and scar formation process occurs over months or even years.
Oh, okay, maybe let's get back to the artificial tissues and start with some existing products. So here on this website, it says that there are existing artificial tissue products for skin grafts, nerve grafts, vascular grafts, and cartilage implants. Most are designed to accelerate or assist the body in self-healing.
Which of these factors is more important in determining the healing capability of a tissue? That is, both influence the healing process, but one is more important than the other. Which is it? Emma and Paul discussed this earlier in the chapter. Go back and have a look. Are you interested in an example of tissue regeneration and why tissue engineering could play such a major role in future therapeutics? Watch this video by Professor Engel.
My name is Professor Felix Engel, and I am an expert on heart regeneration. My research focuses on understanding how the heart forms during development and what causes underlie different heart diseases in order to develop novel strategies for therapy. For example, we're interested in cardiac tissue engineering, where we combine stem cells with different materials to engineer heart tissues that we can use for therapy. Well, it is important because heart diseases are among the leading causes of death worldwide. Heart disease affects not only adults, but also children, as congenital heart disease affects around 1% of all newborn children. So if you study heart development, you will realize that the heart grows mainly based on the proliferation, the amplification of the contractile cells of the heart, the so-called cardiomyocytes. But around birth, these cells stop to proliferate, and the heart grows only by, or mainly by, the fact that the individual cardiomyocytes just become bigger. Now, this means when you have an injury like a myocardial infarct, where a large part of your muscle dies, we are not able to generate new cells, and also the cells cannot become any more bigger, and therefore the heart cannot regenerate. The same problem we have with the children that have a congenital heart disease. In order to repair these defects, they need the surgery, which requires also to remove part of the muscle tissue. And again, these children have not the ability to generate these new cells because cardiomyocytes cannot proliferate anymore. And therefore, we have either to find ways to stimulate the proliferation of the cardiomyocytes, or we are able to engineer artificial heart tissue that then can be transplanted to improve the function of the heart of the patients. Well, in order to engineer cardiac tissue, you first have to know what kind of cardiac tissue do you want to engineer. The heart is a rather complex organ that consists of 4 different chambers: the large vessels like the aorta, as well as the coronary vessels that supply the muscle itself with oxygen and nutrients. And there's also heart valves. So the most important in terms of cardiac tissue, meaning the muscle tissue, it's important to realize that each chamber has a different composition of cells. So they are not only the cardiomyocytes, but also fibroblasts, or the vascular cells, endothelial cells, and smooth muscle cells, and even immune cells. So macrophages play a major role in the heart. And this composition is different in each of the chambers. And not even that, there is even a difference in the cardiomyocytes itself. So what we need is the right composition of these different cell types. But a muscle is not only cells, so you need also a matrix. So all the cells are kept together with the so-called extracellular matrix that consists of proteins like collagens and laminins, but also glycoproteins like hyaluronic acid. And so therefore, when we engineer tissue, we need the cells, but also a scaffold, a matrix that we have to engineer. So in the end, we have to combine our knowledge from cell and developmental biology in regards of the cells. We have to combine it with materials that kind of resemble the extracellular matrix. And then we need engineering processes that allow us to combine this to engineer in the end exactly that tissue that is missing or that should be replaced in the patient. Well, today we can already engineer really tissues. So we can make a contractile tissue that really in a cell culture dish is beating, and we have even already transplanted those tissues in small and large animal models of different diseases, and can show that it improves the function of the heart. And there's even the first clinical trials that test the suitability of those tissues for transplantation. Now, the problem, however, is that if we look at these tissues, they are not yet as contractile as we want them to be. So one problem is that these cells, the stem cells that we use to make cardiomyocytes, can be produced in large numbers, and we can also differentiate them very efficiently in cardiomyocytes, but they do not become adult-like. So they stay somewhat like heart muscle cells when you were born. So meaning they have not such a strong force that they can develop. And the second problem is that the tissues that we engineer are usually rather thin and not thick tissues because you need the vascularization for that in order to keep the thick tissue alive. And this together kind of adds up to the problem that we have beautiful contracting tissues that, however, do not exhibit the contractive force that we need to really improve the heart function of the patients. Now, we see positive effects, but it's mainly believed that they are due to a mechanical stabilization of the heart. And that is also supported by the fact that if we transplant kind of only the scaffolds without the cells, we also see a positive effect. But nevertheless, we can make tissues, we can transplant these tissues. The results are very promising, not perfect yet, but I am very optimistic that we solve also the problems of vascularization and differentiation to get more dot-like cells within the next 20 and 30 years. But it might be that in this time frame, we actually have achieved to develop a novel strategy to repair the heart for children as well as for adults. Well, thank you very much for having me. It was my pleasure. I hope I could give you an insight in the field of cardiac tissue engineering and demonstrate that this is an exciting and promising field for the future, and wish you all the best with your studies.
Okay, so there's skin grafts, nerve grafts, vascular grafts, and cartilage implants. Maybe we should just pick one as an example to learn from.
Well, I think the most well-established type of artificial tissue implant seems to be the artificial skin grafts.
Okay, let's use artificial skin, but let's start with some basic information about skin. So skin has 3 layers: epidermis, dermis, and hypodermis. After the occurrence of an acute wound to the skin, there are 4 steps to wound healing: blood clotting, inflammation, new skin growth, and new skin remodeling. Cytokines are secreted by different cells in the blood to recruit different cells at each step. Maybe that's why healing is repressed in burn victims, because the blood cells are damaged and they can't recruit new cells anymore.
Maybe we can find another video on that on Professor Scheibel's page. Yeah, here's one. Let's have a look.
All right.
Hi, today we're going to talk about biomaterials and wound dressings. But first, I should introduce myself. I'm Sally Mcarthur. I'm a professor of biomedical engineering and the director of the Manufacturing Futures Research Institute at Swinburne University of Technology, which is here in Australia, in Melbourne. I'm really passionate about how we make biomaterials into things that you can buy when you go to the supermarket or when you need a medical care. So what we're going to talk today about is some of the challenges that come together with actually turning all the things that we do in the lab into new products that you can buy yourself. So before we start, I just want to acknowledge that I am sitting in Australia, and on the behalf of those present, I want to acknowledge the Wurundjeri people of the Kulin Nation, who are the traditional custodians of the land on which I'm sitting here in Australia. I pay my respects to their elders, past, present, and emerging. So when we think about biomaterials, really I think about how they connect biology in our bodies to technology. And so here in this image, we can see some great examples of how that works. We've got a artificial arm where it's going into the skin layer, and there's sensors on the outside of the skin as well. So there's a combination of things that go inside your body and things that sit and interface with your skin. There's a heart pump there, so they can't get more intimate than that. And the types of things that we really have to think about in how mechanically that works, but it's coming in contact with all of your blood, and it's biointerface engineering actually. So the surface of the material that has a really big influence there on how your blood might clot. And that's the area of research that I really specialise in. So what does that have to do with making a wound dressing? Well, if you think about it, it's where your skin heals and the things that we put in contact with that wound on the surface of your skin that actually help it heal. So you can think about it like a Band-Aid in the example here in the photo. But if you think about what happens when wounds actually heal, there's quite a complicated process. There's the blood clotting, you get fibroblasts and macrophages coming in to heal, and you get a scab formation. And then you get all the fibroblasts producing all the collagen and repairing it. And then in that final stage, you'll heal the epidermis and heal the dermis. So it's quite a complicated cascade of events. And it's really heavily influenced by the nature of that tissue. So older tissue might take longer, or it might break more easily as well. But there are also a number of situations, including one of the biggest today, which is diabetes, where you can get to this horrible situation where wounds just don't heal. So these non-healing wounds can remain open and exposed or needing dressings every day for months and months and months. They're generally related to pressure, but in the diabetic case, what you get is poor blood supply and loss of nerve. So you can't actually feel it. It's not necessarily painful, but it's an open wound, and we know what bacteria like to do. They love to infect open wounds. So if you get bacteria in that wound, you run the risk that you will actually get septicemia or more damage to that tissue. So for most people with diabetes and these types of long-term non-healing wounds, we need a different solution. We need to upgrade the Band-Aid. And we really want that upgrade to really do a range of different things. We want it to actually help heal the wound. How do we actually do that? We need it to fight the infection. Perhaps in the case that I've got here, that wound isn't just on the surface of your skin, it's actually quite deep because the damage has been done over time. And so by the time you get to it, you might need to fill that wound as well, actually provide something for tissue to grow into because there's too big a space to fill. At the same time, we want to actually capture the good things that your skin is trying to do in repairing and use them and get rid of all the bad stuff. The other thing that's really important in diabetic wounds is because that problem is there because of the blood supply is poor to that area, we actually need to stimulate the blood supply there as well. It's pointless putting in lots of really good things if there's no blood supply to keep the new tissue that you're going to try and form alive. And that's really important. So in terms of thinking about a wound dressing, these are all the things that you might want to put into that. But as an engineer, I also like to think about how we might actually, what are the challenges of actually making it in that way? Now, of course, our first challenge is that everybody's different. In our populations of people, there are lots of different skin types, there are lots of different health levels, and the way that somebody's physiology actually reacts to an active wound dressing like this is going to be very different. The other one here in this glove testing example is trying to show you is how do you scale up that manufacturing? How do you make it and test it to make sure that it's going to work every time? And how do you then make sure that it doesn't interact too much with bacteria, that it doesn't become a place that the bacteria really like to be, which is just going to make the wound worse. The other thing is we need to think about how long it's going to stay on that wound. Is it going to be put on and off every day, or is it going to need to stay on for a week or a month at a time, or is it never going to be replaced? Is it going to degrade and replace the skin and break down over time? And that really helps us decide the materials that we're going to make it out of. And the really important thing there with the materials is thinking about how do we actually turn them into something that can go on to that wound and stay in place? The biggest issue, of course, though, is how much is it going to cost to make? I can make you something that will do all of those things, probably, given enough time and enough money. But will I ever be able to actually turn it into a dressing that you could buy? And so they're all the really important things that we need to think about. And they're the problems that are actually facing us today. There's so much more to do in this field of wound dressings. We've got scientific, engineering, and healthcare challenges that we need to really understand to create new products. We need lots of different insights. We need to work in teams with people who have different knowledge about the manufacturing, different knowledge about the biology, but also different knowledge about how we look after non-healing wounds, nurses, people who are out there dealing with patients who have these. And the other thing that makes it, I think, really important is there's more and more people every day who are being diagnosed with diabetes and other diseases that can cause this type of non-healing wound. So we have an increasing population who need these types of treatments or will need these types of treatments in future. I hope that explains to you a little bit more about how biomaterials and wound dressings come together. I look forward to seeing you another time.
What additional considerations do you need to make when treating a pathological wound as compared to a healthy wound? Select all that apply. If you're not sure, watch Dr. Mcarthur's video again.
So basically an artificial skin graft should protect the wound from further injury or infection and stimulate healing.
You know what? We've been talking about artificial skin this whole time, but skin replacement actually dates back to the Second World War, where they started using skin grafts to...
Okay, Paul, we're losing you. Please focus.
Come on, what happened to your previous admiration? Like calling me a self-motivated learner.
Well, you know, even good things should be done in moderation, Paul.
Okay, fine. Let's find the most common artificial skin products and wound dressings and compare them.
Thank you. Okay, so it seems like popular products are Transcyte, Integra, and BioBrain. Integra and BioBrain are cell-free and guide tissue regrowth. Transcyte is a new variant of BioBrain.
Okay, and what are the scaffolds made of?
BioBrain is a knitted nylon mesh coated with porcine collagen that is bonded to a thin silicon membrane. The silicon membrane is the new epidermis, and the nylon mesh supports the wound area mechanically. Apparently, it's one of the first artificial skin grafts ever made.
What happens to it then over time? Do you just have nylon and silicone in your skin forever?
Good question. Here it says it can be removed later or will naturally separate from the wound as it heals. It also says that it can only be used for partial thickness wounds or burns. Apparently, Transcyte can be used in full thickness wounds as an alternative to an autograft. It is the same basic product as BioBrain, only they culture neonatal fibroblasts, which then create their own matrix.
That's really good. So they wouldn't have to cause secondary injury by taking skin from somewhere else.
Yeah, but here it says that the problem is that it is significantly more difficult to store and much more expensive than other artificial skin grafts. It's 13 times more expensive than an autograft.
That's less great news, but why is it so expensive? Do they have to keep it in an incubator the whole time?
Nope. They have to preserve it at minus 70 degrees and bring it up to 37 and directly implant within 18 months of the product being made. I think it is expensive because everything they need to make it is expensive, whereas with the autograft, they only need to pay the surgeon for their time. And the skin itself does not cost anything.
This Integra product seems fairly different.
How so?
Well, it is a permanent implant that does not need to be removed, except for the silicone dressing that they have on the top to protect the wound in the first 2 to 3 weeks. However, the dermal substitute is made completely of biopolymers, so it can biodegrade. It's a fibrous, porous matrix that is a combination of bovine type 1 collagen and shark cartilage. Oh, this is a mouthful. Chondroitin 6-sulfate and glycosaminoglycan.
What?
Apparently we can call them GAGs.
GAGs are critical for water retention and sequestering growth factors. I recommend that you watch this video and learn more about them. In this chapter, I would like to give you an introduction into glucosaminoglycans. These are polysaccharides. Polysaccharides you probably know as sugars. Typically, we use monosaccharides, individual building blocks, and if we multimerize them, we call them polysaccharides. That is pretty much akin to what we learned about polymers, where we have the polymerization of individual monomers. And like with polymers, you can have single sugars that are polymerized, or you can have several ones like with the copolymers. If we look inside the human body, there, polysaccharides also play a very huge and important role. The polysaccharides that are used inside humans, they are called glucosaminoglycans, or in short, GAGs. I just will call them GAGs from now on. GAGs are very important for a lot of applications, and the most established ones are in cosmetics. So GAGs are used in a lot of skin creams, face creams, and so on, because they can hold a lot of water. They pretty much perform like hydrogels. So I would like to remember how hydrogels work. They can hold up water, they can release water, and therefore they're moisturizing the skin. But they're also important in tissue engineering, especially in orthopedics. GAGs can also be used actually as drug delivery vehicles, because low molecular weight GAGs can actually use as a naturally derived drug. The most important GAG you probably have heard of is hyaluronic acid. Hyaluronic acid, or HA, can promote angiogenesis. The general structure of a GAG is made of the multimerization of disaccharides. So the building block is not a single sugar, but it's a pair of 2 sugars. And these 2 sugar units are then repeated over and over. Typically, one of these units is a uronic sugar, and the second one is the amino sugar, and this is what gives the GAG its name. In most cases, GAGs have sulfated side chains, but the sulfitation is very specific to these GAGs and the sugars because we don't find this process in any DNA template. It's an enzymatic driven process. Where do we get the GAGs from? For the applications, for instance, in cosmetics, well, for that, natural raw materials are used because GAGs are not only found in humans, but also in animals. But GAGs can also, to some extent, be produced by fermentation, so in biotechnological processes, where we combine bacterial production and then post-translational enzyme systems to actually fine-tune the structure of the GAG. As mentioned, the most well-known example is hyaluronic acid. Hyaluronic acid is also one of the shortest and smallest GAGs and one of the most simplest ones. It's also called hyaluronan, and it's an anionic, non-sulfated glucosaminoglycan which is distributed widely throughout our connective, epithelial, and neural tissues. So the non-sulfated state is really outstanding because all other GAGs have sulfated sugars, but the HA has no sulfated sugars. What is so special about hyaluronic acid, and why is it used, for instance, as a dermal filler? The water binding abilities of HA are really outstanding, and therefore it can be used to moisten our skin and cartilage tissues because this is the native function of it. But also as a dermal filler because it swells like a hydrogel, and therefore it's perfectly suited to fill out dumps, for instance, in our skin. What is the role of proteoglycans in general? Well, first we have to consider what is a proteoglycan. So there we have a protein which is combined with a sugar. Then we call it proteoglycan. And along these sugar chains that are associated with the protein, now we find as a further modification the GUCs. And here you see one of these examples where we have a tiny little core protein, and then we have a long chain of sugars on which then all the GUCs are adapted to. Therefore, we get now a huge network, and you can imagine that the proteoglycans really resemble naturally occurring hydrogels, so to say. And this is one of the roles: taking up water, filling up the space in between cells and tissues.
Well, let's call them gags then.
Essentially, it is supposed to guide cell growth and stabilize the wound. But unlike BioBrain, the cells should remodel the artificial matrix and mature into tissue. Apparently, it's pretty effective.
So they all seem to have their pros and cons.
More or less, yeah. You know what? Why don't I draw this out?
What is the most significant advantage and disadvantage of each of the types of skin replacements we discussed? Consider what is shown in the drawing and go back and watch the video segment if you're not sure.
Now,
No wonder that there are not a lot of artificial tissues that are approved for implantation. This whole thing seems very complicated. I guess the best one to